Okay, as you guys said, we are transferring electrons. So somebody gives an electron, somebody takes an electron. We call that a couple. Now you add an oxidation reaction to a reduction reaction, you get the cell. Okay, we call a battery a cell, okay, which is an anode added to the cathode. So before we get into all of the, down and dirt, to the nitty gritty, let's balance an equation. Okay, how many of you have balanced equations in Chem 1? Okay. All of you should have raised your hand because all of you have balanced equations in Chemistry 1. But we're going to balance a redox equation. So first and foremost, I want you guys to pay particular attention to this. Okay, so we're going to balance this redox reaction in acidic medium. So you can balance it in acidic medium, you can balance it in basic medium, but we're going to balance it in acid. We're going to balance it in acid. So when we balance it in acid, what two things do we have in a lot of abundance? Let's see, what two things do we have a lot of in acid?
H2O and H3O plus.
Yes. Okay, instead of H3O plus, Bailey, I'll just call it H plus, but you're right. H plus, you're right. Okay. The way I'm teaching it, H plus is H3O plus, same thing. And yeah, she's 100% right, H2O. Okay. All right, so in basic and medium, what will we have, Bailey? Water and not H plus, but
H3O. Oh, basic OHO.
yes, okay. So on your homework or your next chemistry class, okay, if you're asked to balance in basic medium, you'll have water and H2O. Okay, H2O is just the solvent of life. Okay, everything happens, all our reactions happen. I teach biochemistry. Everything happens inside water. Okay. All right, so we're going to break this down. Okay, we have Fe plus 2. We're going to break it down, deconvolute. Deconvolute just basically means we're going to break it down, split this apart into oxidation and reduction. All right, so the first thing is we have Fe plus 2 going to Fe plus 3. Okay. So what did we say we transfer in a redox reaction? Not protons, but electrons. Okay, so question for you guys here. We got one Fe here and one Fe here. Okay, that's good. We have a plus 2 here and a plus 3 here. Okay, so what do we need to do to balance the charge? Okay, what do we need to do to balance the charge with electrons? Okay, with electrons. How many and where? All right, I'm going to put one electron here in the product side. All right, so everyone look at me. The reactant is plus 2. And what is the charge on the product side? 3 minus 1 is?
2.
Plus 2, plus 2, plus 2. Okay? So I have balanced this. How many Fe's here? 1. How many Fe's here? Iron? 1. Now, question. Is this an oxidation or a reduction? This has lost one electron. In order for Fe plus 2 to go to Fe plus 3, what has it done? It has lost an electron. How many? 1. So is this an oxidation or is this a reduction? Is it oxidation or reduction? Okay, here's another thing you may have heard, Leo Gur. Okay, lose electrons, oxidation. Gain electrons, reduction. He's my friend, Leo Gur. Okay, lose electrons, oxidation. Gain electrons, reduction. So coming back to our problem here, this has lost one electron. So is this oxidation or reduction? Lose electrons, oxidation. This has lost one electron. This is an oxidation. So if this were a battery, what would this be? Would this be the anode or cathode? Here you want to remember red cat eats an ox. Red cat red cat eats an ox. Reduction occurs at the cathode. Eats an ox. Anode oxidation. Anode oxidation. So oxidation happens in the where? Anode. Okay, now we have MnO4 minus goes to Mn plus 2. MnO4 minus goes to Mn plus 2. All right, let's write this out. Just write it out here. Right. So we have 1 Mn, 1 Mn. Okay, this is permanganate. That's the name of this ion, but this is manganese, Mn. So we have 1 Mn, we have 1 Mn. We have 4 oxygens. Okay, it's crazy. Okay. What will we do to balance out the oxygens? Okay, remember as our classmate Bailey told us, what do we have a lot of in acidic medium? We have a lot of hydrogen ion and water. So I'm going to balance the oxygens with water. And how many waters? Okay, 4. Okay. This will balance out my oxygens. Okay, now I have 8 hydrogens. How will I balance out my hydrogens? Okay, remember what Bailey told us? What do we have a lot of in acid? We have a lot of water, and we have a lot of H+. So I'm going to balance the hydrogens with H+. I'm going to balance it with 8. 8 H+. We can do this because this is an acid. Right, now we're going to balance the charge. Okay. So everyone look at me here. Plus 8, or look at the screen, or whatever. Look at just pay attention. Plus 8. Okay, plus 8 minus 1. What is that? 8 minus 1? Plus 7. Okay, here we have a plus 2 in the product side. Okay, so we will balance it out with electrons, but how many E minuses do we need to balance it out? And where? Okay, so let me give you a hint. If this is oxidation, this top one here, what will the bottom one have to be just by default? Just by default, it will have to be reduction, because oxidation, reduction. Okay, they are a couple. The question is, where? So it's going to be reduction. Where are the electrons in a reduction reaction? In a reduction reaction, you gain electrons. So it's going to be in the product side. It's going to be in the reactant side. It's going to be in the reactant side. But how much? What do you guys think? Plus 7 here, plus 2. Okay, so it's going to be 5 electrons. So this balances out that half reaction. Okay, just cross this out here. All right, so this is reduction, and this is where the cathode happens. Here we're gaining 5 electrons. MnO4 minus to become Mn plus 2, it's gaining 5 electrons. So this is a reduction, and reduction occurs where? Okay, at the cathode. Okay. right, so we got our reduction, we got our oxidation, okay? And now what we will do is we'll add them up, okay? But we want to cancel out the electrons. No free electrons, okay? Have you guys heard of free radicals by any chance? No? Free radicals? Never heard of free radicals? So these free radicals are just like free electrons. And if you read the literature, they're actually very bad for your health. And in this problem, we want to get rid of the electrons. Okay, free electrons roaming around are very bad. Okay, there's a disease called ALS. I don't know if you heard of ALS. Okay, it's free electrons roaming around, damaging the nervous tissue. Anyways, back to this problem. Okay? We want to get rid of the free electrons. So the way we'll do that is we will take this. I will take this top half reaction and multiply it by 5. Okay. When I do that, this is what I get. I get 5 Fe plus 2. Okay, this is going to 5 Fe plus 3 plus 5E minus. Okay, so now we'll add up our reduction with our oxidation. Remember, this is oxidation, and this is at the anode. All right. Okay, I will cancel out the 5 electrons here, and I'm left with my net equation, oxidation reduction coming together, and it's going to be 5 Fe plus 2 plus 8H plus MnO4 minus goes to Mn plus 2 plus 5 Fe plus 3 plus 4 H2O. This should be our correct answer. Let's check if this is indeed our right answer. Let's see if it's balanced. Okay, let's balance out the ions first. All right, 5 ions here, 5 ions in the product side. 8 hydrogens in the reactant side, 8 hydrogens in the product side. 1 Mn here, this is called manganese. 1 Mn here. Okay, 4 oxygens here, 4 oxygens there. Very good. Now the charge. Okay, this is something that always can be worrisome. Okay, how will we balance out the charge? Okay, 5 times 2 is 10. 5 times 2 is 10. 10 plus 8 is 18. 18 minus 1 is 17. Okay, so the total charge on the reactant side is 17. All right, let's look at the product side. Okay, plus 2 plus 15. 5 times 3 is 15. 15 plus 2 is 17. So I am mass balanced and charge balanced. This is the right answer. Okay. You want to make sure you balance out your charges when you balance a oxidation reduction reaction. Let's move on here. Now there's something that you can use on your exam, and that's the reduction potential table. So let me get that out. Okay, now I'm going to teach you how to read this thing. Okay, I'm going to teach you how to read this. First thing I want to tell you is you want to bring this to the test. Okay, so bring to exam. Bring to exam. Now I'm going to teach you how to read this thing. We do not memorize it. Okay, first and foremost, what type of reactions are these? Are they oxidation or reduction? Okay, these are reduction reactions. Okay, reductions, which means what's happening? Are they gaining electrons or losing electrons?
Gaining electrons.
They're what? They're gaining electrons, right? Look, this is gaining 2 electrons. This guy is gaining 2 electrons. This guy is gaining an electron. This person is gaining 2 electrons. We have cesium gaining an electron. So all of these are reduction half reactions. Okay, all of these are reduction half reaction. And look at that word here, standard. Okay, standard. Okay, so these are standard reduction potentials. Potential means volts. And where in a battery do we see reduction? Red cat eats an ox. So this is the standard reduction potential. We can also call this the E cathode. Okay, E cathode. What does that O superscript E naught represent? Standard state. Okay, standard state. Okay, if you need one, it's right here. You want to pass this out, Bailey?
Oh no, I have one right here.
You have one?
I'm just writing. I'm trying to know what you're doing.
What about your classmates? Here. You're funny, I have one. I like her. Thank you. You're a good one. You're funny. I'll miss you in a couple of weeks. We all do.
Well, I'm not back in your class anyway because I am majoring in biochemistry.
Oh, okay. All right, so this is another way of saying E cathode. Okay, E cathode. Okay. Now, this is just common sense, so please think about this with me. Okay, if you have a positive voltage, what does that mean? Are you favoring the products or the reactants? Is it moving forward or not moving forward? When we go to the store, okay, are the batteries we purchase, are they 9 volts, 12 volts, or are they minus 9 volts or minus 12 volts? They're plus, okay? They're plus 9 volts, plus 12 volts. So something like this, look at this top one with me. F2 plus 2 electrons goes to F minus. This is something that's going to happen. This is favored, okay? A negative voltage, think of it as a dead battery. Okay, we don't have negative voltage. In all your life experience, you never go to the store and buy a minus 5 volt battery. Okay?
The day I find out will be the day pigs fly.
Yes. Okay, when pigs fly. Okay, you don't. In all your life experience, you've never seen a pig fly. Okay, so a positive voltage basically just means that this half reaction is favored towards the products. Okay, so that's point one. Okay, point one is all of these are reduction half reactions. Okay, all of these are reduction half reactions, not full reaction, half reaction. All of these are reduction half reactions, which means what? Which means they're gaining electrons. See how they're gaining electrons? This one gained 3. And this one gained 3 to become Au solid. Okay, the second point I want to tell you is that positive voltage means that this particular half reaction is favoring the products. Okay? So a positive voltage favors the products. That doesn't mean the whole battery is favoring the products because we have to combine this with the anode to make the battery cell. But right now, this top one is favored towards the products. F2 would like to gain 2 electrons to become F minus. Okay? So a positive voltage symbolizes or indicates to us that it's favoring the products. What do you think about all the way down, all the way down, all the way down, this voltage here, minus 3.05 volts? What do you think about that? What's your analysis tell you? This ain't happening. Okay? That's like a dead half cell. Lithium, would lithium like to gain an electron? Okay, no. Okay, this is hard to do. Okay, this is hard to do because it's giving you a potential of minus 3.05 volts. Negative voltage is like something dead. Okay? All right, so that's the second important point. Okay? All right, the third important point is this. Okay? Okay, let's look at this reaction right here, this top reaction. Okay, and I'm going to write it down here. This is the third point. I'm going to rewrite it. I rewrote that first half reaction. I can do this with any. I'm just picking the first one. Okay, and we just mentioned this is gaining 2 electrons. Gaining electrons is reduction, and all of these are reductions, standard reduction potential, and reduction happens at the cathode. But I'm going to flip it. Okay, I'm going to flip it. So we said, reading off of the sheet, this is positive 2.87 volts, but I'm going to flip this. Okay, what does flipping mean to you guys? It just means this. Okay. If I flip it, now what happens? I'm going to write the reaction as it's flipped. What do I have here? Is it a cathode now? Is it? Okay, I flipped the reaction. Okay, going from here to here, I flipped it. So I'm no longer the cathode. What am I? What is this half reaction? Notice it has not gained 2 electrons, but what has happened to it? It has lost 2 electrons. So what is this now? Not the cathode, but the anode. Is this still going to be positive 2.87 volts? Okay, it's going to be negative 2.87 volts. Okay.
So whenever like the voltage is positive, it means something's happening, but then when it's negative, it means nothing.
The voltage, if for the cell, because we got to include the anode and cathode together. So the third important rule is that you flip the half reaction. What happens? You flip the sign. Cathode becomes anode. If I flip it again, the anode becomes the cathode. Okay. So we're going to flip. I'm going to flip the half reaction, and then we flip the sign. Okay, that's the next important point here. Okay, how to read this thing. Let me get a nice pen. I don't have pens. Okay, flip the half reaction, flip the sign. Anode becomes cathode, cathode becomes anode. Flip the half reaction, you flip the sign. Anode becomes cathode, or the cathode becomes the anode. Okay, this is important point number 3. Okay, important point number 4 is super important. Okay, so this will lead to a lot of mistakes on the test. Okay, important point number 4 is this. Okay, if I take this half reaction and multiply it by a number, okay, give me a number, Bailey.
10.
I'm going to multiply this half reaction by 10. This becomes just top one, or it can be the bottom one, whatever. Okay. 10 F2 gas plus 20 E minus, multiplying this through by 10, goes to 20F minus. Okay. And now this will have an E cathode. What will my E cathode be? Okay, so here I multiplied it by 10, times 10. What will my E cathode be? Will it be 28.7 volts? Right, multiplied by 10, you'll multiply the voltage by 10. Okay, that's not going to happen. Okay, this is going to remain positive 2.87 volts. Okay? So what I'm trying to say is all these numbers that you see here, all these voltages will not change. They are invariant. What does invariant mean? Invariant means they will not change. What is the only thing that can change with these numbers? The sign. Very good. The only thing that can change is the sign. So all these numbers that you see, you don't mess with them. What's the only thing you can mess with? Their sign, positive or minus. Okay. So all these numbers are invariant. All these numbers are invariant. Okay.
No matter what, they don't change.
Other than the sign. And how can you get these voltages to change sign? Flip it. Okay? Flip it or reverse it or whatever. Okay, so all these numbers are invariant. They do not change. The only thing that changes is the signage, positive or minus. So you can multiply all of these by 10, as Bailey did, 100, or whatever. Okay, it will still be the same. Okay, that's rule number 4. Okay. All right, now comes rule number 5, which is kind of maybe the hardest, but not that hard. Okay, something you have to think about. Okay, so this is standard reduction potential. Okay, this is also called the activity series. Okay, have you heard this term? Activity series? It's another name for this. Okay, remember in our first example, okay, in the last lecture, it was me and Bailey that was giving and donating the electrons. I give an electron and then she takes that electron. Okay, this is a 1 electron transfer reaction. And in this morning class, Eric was the redox couple. I gave an electron, and he took that electron. I become oxidized, he becomes reduced. Now there's a competition. I give it an electron. Who's going to get it? Is it going to be Bailey, or is it going to be Eric? Okay, so that depends on the activity of Bailey, how much she wants this electron, versus the activity of Eric, how much he wants this electron. So all of these are ranked. All of these are ranked based on their ability to take an electron. All of these are ranked in their ability to gain an electron, to receive an electron. Okay. Now, what do we want if we want a battery? Okay. We want our E cathode and our E anode. When we join them together, what do we want? Do we want a positive voltage or do we want a negative voltage? If we want a battery, we want a positive voltage. How will we get a positive voltage here? Okay, so this is what you do. Okay, so I need everyone to be with me. Okay, I want you to pick one, any one of these. Okay, I am going to pick any one. So I'm just going to randomly pick Cl2 plus 2E minus goes to Cl minus. I'm just going to pick this. Okay, you can pick any one you like, but I'm just going to pick this. It's random. Okay, seriously, just random. All right, how will I get a positive voltage? This is the cathode. Okay, I need to combine it with an anode to get a positive voltage if I want a battery. Okay, how will I get that? So this is what you do. Here it is. Okay, you pick one. This is the one I chose. anything below it gets flipped. Anything below it can get flipped. When you flip it, what does this one become? The anode. We combine the cathode, which is what I chose, or what you will choose, with the anode, which gets flipped. That's how you get a positive voltage. So you pick one, anything below it can get flipped. Anything below it can get oxidized. Okay, you see this? So, question for you guys, or something on the exam, let's say. Okay, question, can Cl2 gas oxidize Ag solid to Ag plus? Yes or no? Can it oxidize Ag solid to Ag plus? Yes or no? So this is at positive 1.36 volts. If I flip this, what will this become? Negative 0.80 volts. What's 1.36 minus 0.8? Positive or negative? So the answer is Cl2 can oxidize Ag solid to Ag plus. Anything below it can get oxidized. Anything below it, the one you choose, can get oxidized. Another example, can Cl2, so this can happen. Another example, can Cl2 oxidize Br minus to Br2 liquid? Can it? Yes or no? Can it oxidize? Can it flip the one beneath it? Yes. Okay, this can happen. You'll get a positive voltage. What's 1.36 minus 1.07? Is it positive or negative? It's positive. It's a positive voltage. Okay? So you pick one, anything beneath it can get what? Oxidized. Okay, that is one way to get a positive voltage. This is one way. Okay, what's the second way? Okay, like I said, pick one, anyone. This is the one I chose. Can it oxidize the one above it? Can it flip the one above it? 1.36. If you flip that, the one above it, it becomes minus 1.50. Is this positive or negative when you add them up? Cathode and anode. It's negative. So it cannot flip the one above it. Then how do you get a positive voltage? Okay, the one you choose, you flip that, the one above stays the same. Okay, that's the second way you can get a positive voltage. Okay, so the one you choose, anything above it, keep it the same. The one you choose, flip it. Okay? The one you choose, anything below it, flip it. Keep the one you chose as the same. These are the only two situations where you can get a positive voltage. So, like on the exam, can Cl2 oxidize water to H2O2? Can it? Can it flip H2O so that it becomes H2O2 and gets oxidized, losing 2 electrons? Can this happen? Yes or no? No. Okay, no. This cannot happen. Okay. So the diagonal rule only happens on the one beneath it, the one below it. So let's review here. Let's do one more actually. Can Cl2 oxidize Au, this is gold, Au to Au plus 3, yes or no? No. Okay, how can this reaction happen? How can you create a battery between Au, gold, and Cl? Take this and flip it, keep the AU the same as is. Okay? That is, make this oxidation, flip this, and keep the one above the same. Okay? So this is called the diagonal rule, and this tells us which oxidizes what and what cannot oxidize the other. Okay? So if I were to have our competition between Eric and Bailey, okay, if Bailey was here and Eric was here, if Eric was here, let's say, and Bailey was here, and I am this, I can oxidize Bailey, but I cannot oxidize Eric. Eric can do what? He can oxidize me. So that's what it is. Who can get that electron, or 2 electrons, or 3 electrons? Who can get that better? All right. Once again, you pick one, any one. Let's do one more example here. You pick one, any one you pick. Okay, this is the one we chose. Okay, anything beneath it can get oxidized. Anything beneath it can get oxidized. So Al can be oxidized to Al plus 3 by Fe plus 2. Fe plus 2 gets reduced. But Fe plus 2 cannot, and will not oxidize Sn into Sn plus 2. It cannot. Pick one, anyone, anything beneath it gets flipped. Does everyone understand how to do this thing here? Okay. And let me ask you something here. Okay. This may be a little difficult, so bear this out with me. Okay. I have to think about this here. Can Al solid reduce, I'm saying the word reduce, can Al solid reduce Fe plus 2 to Fe solid? Yes or no? I'm seeing nods, yes or no? You know, in India, I don't know if I can say in India, I don't know about in Asia, but people go like this. You don't know if they're saying yes or no. You know, my wife does that. So the question is, can Al solid reduce Fe plus 2 to Fe solid? Reduce. Yes or no? Yes. Yes. Okay, that's the answer. Yes. Okay, very good. Good job.
So if it's above each direction, it can reduce it, but if it's below it, it oxidizes it.
There you go. Perfect. You said it better than me. If it's above, it stays reduced. Now, can Fe plus 2 oxidize Al to Al plus 3?
Can what?
Oxidize.
Can what oxidize what?
Can Fe plus 2 oxidize Al to Al plus 3?
Yes.
Okay, this is a definite yes. Okay, let's do one more here. Can Sr solid reduce magnesium to magnesium solid? Can it reduce it? Can it reduce it? Yes. Okay. Can magnesium plus 2 oxidize chromium to chromium plus 3? Cr to Cr plus 3. Can it? Can magnesium oxidize? Oxidize Cr to Cr plus 3? No. Okay. This is how you read this thing. Okay. Okay, this is called the diagonal rule, just so you know. So if I were to say the diagonal rule, it goes kind of like this. If I were to, okay. Or it can go like this. Something like that, okay? I don't know. Flip everything below it, keep everything above it the same. Okay, you're right. Reduces everything above, oxidizes everything below. Actually, she said it the best. Okay? All right, let's look at this very top thing here. Positive 2.87 volts. This thing loves to get reduced. It loves. So it is the best oxidizing agent. Okay, let's go back to our example with me and Eric. I give one electron. He takes it. Okay, he is the agent that causes my oxidation. See, he gets reduced. He took my electron. But in turn, what did he do to me? He oxidized me. So he is the agent that caused my oxidation. He is the agent that caused my oxidation. So we say here that this is the best oxidizing agent. Look, it can oxidize anything below it. It can. It can oxidize this whole sheet, this whole list down the column. So this is the best oxidizing agent in this table. Remember, it is air getting reduced is the agent that causes my oxidation. So this is the best oxidizing agent. It can flip everything beneath it. Okay, let's go all the way down here. Okay, this is the best reducing agent. You see, I gave an electron and I become oxidized. Okay, I become oxidized. I am the agent that caused Eric's reduction. Even though I got oxidized, I reduced him. I am the agent that causes his reduction. I am the agent that caused his reduction. I get oxidized. So this is the best reducing agent. So it's kind of backward, which can be a little bit confusing, but the best reducing agent is me, because I'm the one that can reduce you, and you. Okay? In fact, look, this can actually, remember, anything above it stays reduced, as Bailey said, so this can keep everything above it reduced. Okay? This at the top flips everything below it oxidized. Alright, so this is the standard reduction table. You can bring this, take this to the exam. I have clean copies also. But whatever it is, bring it to the test. Alright, let's go now to page 2 here. Page 2, yeah. All right, so there's a new notation that I want to teach you now. Just look at this for a moment. I have a beaker with zinc sulfate, which is zinc plus 2, SO4 minus 2. Okay, I got some zinc solid here, a zinc strip. I got this in one beaker. In a totally separate beaker, I got a liquid or a solution that is copper sulfate. Which is copper ion and sulfate ion, and I have a copper strip. connect these two beakers, these are kind of incommunicado. Okay, the only way they can be in connection with one another is what's called a salt bridge. Okay, a salt bridge, which basically makes sure there's no buildup of ions in this beaker or no buildup of ions in the other beaker. Okay, that's all you need to know. Okay, it does not allow the accumulation or buildup of excess positive charge here or excess negative charge there or wherever. Okay, so salt bridge has this symbol, 2 lines. Okay, 2 lines, we're going to call that a salt bridge. All right, so look what's happening. If you look at this picture diagram, if you look at this diagram, you actually see the zinc giving away 2 electrons, and those 2 electrons going down this wire and going down to the copper solid. Okay, so that's what's shown in this diagram, in this picture. So, what does this mean? It means the zinc is losing 2 electrons. Okay, let's write that out. The zinc is losing 2 electrons. Coming back to our table here, let's look at zinc. Okay, zinc losing 2 electrons. Here, zinc is gaining 2 electrons. But what's happening in our diagram? Zinc is losing. You see the 2 electrons exiting? It's going down this wire. Okay, so we have zinc losing 2 electrons. So this is gaining 2 electrons. Okay, what's happening in the diagram is they're losing 2 electrons. I'm going to flip this. So what we have on this side is zinc solid. I'm just copying it down but flipping it. This is what's happening here. Okay. This is not minus 0.76, but what is this voltage? I flipped it. Positive 0.76, reading from the table. Why did I flip it? Why did I change it from negative to positive? Because this is losing 2 electrons. Okay, what's happening in this diagram here on this beaker, the right hand? We have copper gaining 2 electrons. Let's see what's happening here. Copper gaining 2 electrons. Okay, this is what's happening here. We have copper plus 2 gaining 2 electrons going to copper solid. This is what's happening here. Copper plus 2 right here gaining the 2 electrons going to copper solid. Okay, so the 2 electrons are going to copper plus 2, giving us copper solid. And what's the voltage associated with that? Positive 0.34 volts. Will I change this sign? No. Okay. So that's what's happening in the green. This is what's happening in the black beaker. Is this oxidation or reduction? This is oxidation. Oxidation happens at the anode. Is this oxidation or reduction? This is reduction, gaining 2 electrons. Reduction occurs at the cathode. Okay, we add these 2 up, we get E cell. We add these 2 up, we get E cell. How many electrons are being transferred here? Okay, this is a 2-electron transfer reaction. Okay, you see the 2 electrons cancel out, so this is a 2-electron transfer reaction. So our E cell is going to be this, copper plus 2. plus zinc solid is going to go to zinc plus 2 plus copper solid. Okay, the E cell, when we add the anode and cathode, is going to be 1.10 volts. Okay, so this is what you will see on the voltage reader, 1.10 volts. Is this spontaneous, or does it favor the products? Yes. So you can make a battery out of copper and zinc. Okay. 1.10 volt battery. Okay, that's E cell, combining the anode and the cathode. So on the exam, I want you to switch between this, which is the net redox reaction, combining the anode and cathode, to this. Okay, this is called the galvanic cell notation. Galvanic cell notation. Right, so the anode couple. Okay, what is the anode here? Zinc, so this is what you're going to write. You have zinc solid. You're going to draw one line down, goes to zinc plus 2. Okay, salt bridge. Okay, we said a salt bridge is 2 lines, 2 vertical lines. The cathode couple. What's the cathode couple here? Copper plus 2, draw a straight line down. Going to copper solid. Okay. So on any exam, okay, these 2 lines are the salt bridge. You should be able to go back and forth. If I give you this, okay, you should get the equation. If I give you the equation, you should get this. If I give you this, you should be able to convert it to that, which is the anode, salt bridge, cathode couple. If I give you this, the galvanic cell notation, you should get the equation, the redox reaction. Okay, so basically, just be comfortable going back and forth between these two. Okay, once again, this is the anode couple. These 2 lines represent what is known as the salt bridge, so that there's no accumulation of excess negative or excess positive charge. And then finally the cathode couple. So that is something that we will work on. And then, yeah. Okay, the next couple of pages are review, so I'm going to kind of hit them fast. All right, so we have the galvanic cell notation. Just make sure you are comfortable with that. And so the way I'm teaching it to you is a certain way. If you want to use the textbook, they have a different way of instruction. I'm telling you to flip. The textbook doesn't tell you to flip. It tells you to do this. So, if you want to look at the textbook or the OpenStax book, they have their own way of getting the E-cell. So either you can use the textbook or you can use what I'm teaching you now. And then, yeah. Okay, a little bit about the diagonal rule. Yeah. Okay, again, pick one. Anything below it gets oxidized. Anything above it remains reduced. Okay? This is from the textbook explanation. And then, positive voltage I want you to associate with something that's going to happen spontaneously. Okay, so the previous example, this is going to favor products. Why? Because it's positive 1.10 volts. If it was negative 1.10 volts, it would be a dead battery. Okay. And then page 4 here, this is the same thing that I told you about on the the table there that you can bring to the test. You don't change the numbers. Okay, what can you change? Sign. And what happens when you change the sign? How do you change the sign? You flip the reaction. Okay, you don't change the number. Okay, just change the sign. Okay, if you flip it and make it cathode, or you flip it, make it anode, whatever, okay, you're just changing the sign. Okay? If I multiply by 10, what happens? It still remains the same. Okay, here we multiplied it by 2. We can multiply it by 10, we can multiply it by 100. That number is invariant. Okay, invariant. What you see in that table is invariant. Okay, so that's page 4. Okay, page 5 is the diagonal rule. Okay, I think she said it best. I'll keep referring back to your classmate Bailey. Okay, anything above it remains reduced. Anything above it remains reduced. Anything below it gets oxidized. Okay, whichever one you choose. Now we'll just finish the rest of the class with some problems, okay? All right, so what are we on here, page? All right, we'll do this one together, and then I will end the class. Even though the solution is out here, we'll do it together. And that will be the last part of today's class. And then I want to finish this Thursday, and then where we are done with the class officially. Okay. So, so what is the EMF of a galvanic cell? Okay, EMF stands for electromotive force. Okay, it's just a fancy way of saying voltage. Electromotive force. It just means voltage. Okay. What is the electromotive force of a galvanic cell made of a cadmium electrode and 1 molar cadmium nitrate? So cadmium nitrate is Cd plus 2 NO3 minus. And a chromium, Cr is chromium, electrode in a 1 molar chromium nitrate solution. So chromium nitrate is Cr plus 3 and NO3 minus. Okay, so what is the voltage between the cadmium and chromium? And then spontaneously, I want you guys to highlight the word spontaneously. So what are we looking for when we say spontaneously? Okay, we're looking for a positive voltage. Okay? Positive voltage. All right, so first we have cadmium. Okay, cadmium nitrate, which is cadmium ion. So let's first do the cadmium here. Let's look at our table. Okay, where do we see cadmium? Where do we see cadmium? Oh, I see it. Cd plus 2E minus goes to Cd solid. See that? Okay, so I'm going to write this down. Cd plus 2 aqueous plus 2E minus goes to Cd solid, and that's minus 0.40 volts. All right, and then let's look at the chromium one. Okay, chromium. Where's chromium in our sheet? Anybody, can you find it? Where is it? Is it even here?
It's right above the
Two
zero.
down on the last.
Ah, two down. Thank you. Two down. You're right. Okay. Okay, chromium. Okay, Cr. I'm going to write this down. Okay, we have to flip one. Cr plus 3e minus goes to Cr solid. This is minus 0.74 volts. Cr plus 3e minus goes to Cr solid, and this is minus 0.74 volts. Okay. Okay, so we have to flip one, and the other one we maintain the same. We got these from our table. We want it to be spontaneous. Okay, so spontaneous should tell us that this should happen on its own. So that means a positive voltage. So which one should we flip? The blue one or the red one? The blue cadmium or the red chromium? Okay, we will flip the bottom reaction. Okay, so flip bottom half reaction. This will make it an anode. So this is going to be Cr plus 3e minus goes to Cr solid. This becomes positive 0.74 volts. It's the anode. Okay, next up, we'll keep the bottom one the same. We'll keep it as the cathode. Okay, we have to flip this, so I didn't flip it. So I'm just being rushed for time. Okay, this is positive 0.74 volts. Okay, this is the anode. Okay, this cathode will be the same as Cd plus 2e minus goes to Cd solid. Okay, this stays at minus 0.4 volts. Okay, this is the cathode. Okay, I'm going to multiply the... okay, we flip the bottom one, as Eric mentioned. We will take the top one, multiply it by 2, and take the bottom one, multiply it by 3. This is a 6-electron transfer reaction. Okay, this is a 6-electron transfer reaction. We want to make this positive, so we flip the bottom one to make it positive. Multiply the top by 2. That gives us 2Cr, goes to 2Cr plus 3 plus 6e minus. I multiplied the top by 2. What will this voltage become? Stays the same. I multiply the bottom reaction by 3. What will the voltage be? The same. Okay, this is a 6-electron transfer reaction. And then this is my equation. Okay, what is my E cell? It's going to be positive 0.34 volts. This is E cell. Okay, and that is how we do this problem. Okay, spontaneously, positive voltage. All right, just really quickly, the anode couple here is going to be Cr solid, one line down, Cr plus 3. Salt bridge is 2 lines. The cathode couple is Cd plus 2. Draw one straight line down, and then Cd solid. Okay. So we will take the rest of this chapter doing practice problems like this. So we'll try to get ourselves comfortable in doing these problems. And yeah, okay, that is our goal for Tuesday. What is it? Thursday and then Tuesday, right? Thursday and Tuesday. Okay. So I think we have time to get some practice in and our practice test in. All right, I went overboard, so thank you for your patience. I'll see you all on Thursday. I'll see you some in lab also.